All right, Venkat, this one is just for you. We are going to absolutely crush this chapter on chemicals and chemical changes. My goal is to get you so ready that you walk into that exam feeling like a total science superstar. You ready? Okay, let's do this.
So just think about it for a second. A shiny gold bangle, a plastic basket, even a simple glass of water. I mean, they seem about as different as you can get, right? But here's the secret. They have one huge thing in common. They're all made of chemical substances. And trust me, by the end of this, you're going to see exactly how. So here's our game plan for today. Think of it as our roadmap to acing this thing. First, we're going to figure out what everything is actually made of. Then we'll crack chemistry's secret code. After that, we'll learn to write some chemical recipes, see reactions happen right in front of us, and finally, we'll nail the difference between permanent and temporary changes. Let's get right into it. Okay, first things first. Before we can do any of the cool stuff, we have to understand what everything, and I mean literally everything you can see and touch, is made of. We're talking about the absolute fundamental building blocks of our world.
It all, and I mean all, starts with the atom. Imagine it's the tiniest possible Lego brick of any substance. You can't get any smaller than that. Now, some atoms are happy to be alone, but most, no way. They need to team up to join together with other atoms. And when they do that, they form a molecule. And molecules can't exist all by themselves. So remember that. Atoms build molecules. Simple as that. So how do we organize all this stuff? Well, you've got two main groups. On one side, you have elements. Think of gold. It's totally pure, made of only one kind of atom. You can't break it down into anything simpler. But on the other side, you have compounds. This is where the magic happens. It's what you get when you chemically combine two or more different elements. Water is the perfect example. You take hydrogen gas and oxygen gas, and poof, they combine to make liquid water, something with brand new properties. That's the key to a compound. It's a whole new substance. But wait, there's one more category. Mixtures. And this is different. In a mixture, things are just stirred up together. They aren't chemically bonded. Each part is just hanging out and keeping its own identity. A great example is if you mix iron filings with sulfur powder. The iron is still iron, a magnet will pull it right out, and the sulfur is still that yellow powder. They're just mixed, not changed. Okay, you're doing great. Let's move on. Imagine having to write out hydrogen or oxygen or carbon every single time. Ugh, so slow, right? Well, scientists thought so too, so they came up with a kind of secret code for chemistry. These abbreviations are called chemical symbols. You can just think of them as the official nicknames for every element. And a little fun fact for you, the modern system we use today was really perfected by a Swedish chemist named Jöns Jacob Berzelius. A great name to remember for a bonus question, maybe. Now listen up, Venkat. This slide is super important for your exam. Most symbols are pretty easy, you know, H for hydrogen, O for oxygen. But look at sodium. It's Na. And iron is Fe. What's up with that? Well, it's because their symbols come from their old Latin names, natrium for sodium and ferrum for iron. That's a classic trick question, so don't forget it. Okay, here's another one of those key words you're definitely going to see, atomicity. It sounds really complicated, but it's not. It just means how many atoms are chilling together in one molecule of an element. Some elements are total loners. Their atomicity is just one. But others, like the oxygen we breathe, always travel in pairs. That's why we write it as O2, and we say its atomicity is 2. So we have our symbols, which are kind of like our ingredients. Now, let's learn how to write the recipe. And really, that's all a chemical formula is. It's a recipe that tells you exactly which elements you need and exactly how many atoms of each. Now, to write a perfect recipe, you need to know the secret number. And in chemistry, that secret number is called valence. Valence is basically the combining power of an atom. It tells you how many hands it has to link up with other atoms. Getting this right is the absolute key. So how do we use valency? With this awesome little trick called the crisscross method. Let's do carbon dioxide together. Step 1, write the symbols, C and O. Easy. Step 2, write their valencies right below them. That's 4 for carbon, 2 for oxygen. Step 3, now you just crisscross. The 4 from the carbon goes to the oxygen, and the 2 from the oxygen goes to the carbon. That gives you C2O4. But wait, step 4 is to simplify if you can. And we can. We can divide both numbers by 2, which gives us our final perfect formula, CO2.
Venkat, I'm telling you, practice this method. You will for sure need it on your exam.
You're on a roll. Now that we can write our formulas, we can start telling stories. And that's all a chemical equation is. It's like a sentence that describes exactly what's happening during a chemical reaction.
So every story has a beginning and an end, right? It's the same in chemistry. The stuff you start with, your ingredients, we call those the reactants. They're on the left. The arrow shows the change, the reaction happening. And the stuff you end up with, those are your products on the right. Reactants become products. That's it.
Okay, now for what is probably the most important rule for equations. You have to balance them. You can't just create atoms or make them disappear into thin air. So look at this example. The unbalanced trie is Mg plus O2 gives you NGO. But hold on, we start with 2 oxygen atoms on the left, but there's only 1 on the right. Where did it go? It can't just vanish. To fix it, we add big numbers in front, called coefficients. The final balanced equation is 2Mg plus O2 gives you 2MgO. Now count them up. 2 magnesiums on both sides, 2 oxygens on both sides. Perfect. It's balanced. All right, Venkat, we're on the home stretch. This is the final section. Let's talk about the 2 main kinds of changes that can happen to substances. This is a classic exam topic, so let's lock it in. This slide right here shows the core difference you need to know. In a physical change, no new substance gets created. Ice melting into water is the best example. It's still H2O, it just changed its form. And you can usually reverse it, right? You can freeze the water back into ice. But a chemical change? Bam! A totally new substance is formed, and that change is permanent. When an iron nail rusts, it isn't just iron anymore. It's a new thing called iron oxide. You can't just unrust it easily. And what's cool is that you see these chemical changes everywhere, every single day. That rusty gate outside? Chemical change. The awesome fizz you get when you mix baking soda and vinegar? That's a chemical reaction, creating a new gas, carbon dioxide. Even when you cut an apple and it turns brown? Yep, that's a chemical reaction too. And one special physical change to keep in your back pocket is crystallization. This is a really neat process we use to get super pure solid crystals from a solution. It's exactly how we get pure table salt from salty seawater. The water evaporates and these perfect, pure salt crystals get left behind. So let's wrap this all up. Venkat, you have just unlocked the basics of chemistry. I want you to look around you today. At a rusting gate, at a cake baking in the oven, at fizz in a soda. It's all chemistry. And now you know the language. You are absolutely ready for that exam. Okay, here's your final assignment. I want you to grab your friends, have them watch this too, and help each other out. Quiz each other. Rewatch this anytime you need a quick refresher. Go on and show them how cool and exciting science can be. You've got this. Now go ace that exam.